Let's talk about graph. In computer science, graph is a very important data structure. A lot of problems can be modeled as graph. For example, a social media, places and their connections, and many more. Graph consists of two sets. One, a set of vertices V, and two, a set of edges E. An edge is a connection between two vertices. Based on whether there is any defined direction on edge, graph can be divided into two types. One, undirected graph, and two, directed graph. Let's look at one example of a graph with vertex set V and edge set E. V consists of 5 vertices and E consists of also 5 edges. These are the 5 vertex of the graph G. We have 5 edges AC, BC, EA, DE, and EC. The important thing here is that the edges do not have any direction. You can write the edge AC same as CA, and it will still mean the same edge. The directed graph, on the other hand, differs from an undirected graph because the edges in the directed graph has direction. That means the edge AB does not mean as edge BA. The first one starts from A and ends at B. The second one is the opposite. That means the order of vertices written in the edge matters. In the directed graph, similar to the undirected graph, we have a set of vertices. And the set of edges E is a subset of Cartesian product of two sets. In our case, the Cartesian product of same two sets V cross V. If we try to draw the graph G, which has a vertex set V and E, but in this time, the graph is a directed graph. Again, these are the 5 vertices of the graph G, but now we have edge AC, but this time we have a direction BC, EA, DE, EC, and CE. Here the edge EC and CE are two different edges. In either case, directed or undirected graph, the size of the edge set E in double bar is the bigger of square of the size of vertex set or bigger of size of the V square. For those who does not remember what the Cartesian product is, let's say for example we have a set V with A, B, C. We have another set U which has 1, 2. So the Cartesian product V cross U is another set which will contain some tuples. The tuple here can be written as two elements using the parentheses. The first element will come from the set V, the second element will come from the set U. So first tuple will be A1, second tuple will be A2, the third tuple will be B1, and so on. Here, the size of that V cross U is size of V times size of U. In this case, size of V is 3, size of U is 2, that means 6. So in our case, for the directed graph, if the size of V is 5, the size of V cross V is 5 times 5 or 25. Again, this relationship can be obtained using some math. So for an undirected graph, we can choose any two vertex to have an edge. So the number of edge can be 0, and the way we can choose number of two elements from the set V. That means V chooses 2, which is here. Previously, we talked about the complete binary tree. Here, we will talk about complete graph. So, an undirected graph is complete when you have edges between every possible two vertices. Let's try to draw a complete undirected graph of 4 vertices. In this case, we have 4 vertices and 6 edges. We can use our previous formula from here to calculate the number of edges. In this case, we have 4 vertex should be the number of edges. One, 2, 3, 4, 5, and 6. Next, let's talk about a concept called degree of vertex. Degree of vertex DEGV is the number of vertices adjacent to the vertex V, or number of edges involving the vertex V. If we denote this vertex V, then the degree of this vertex is 1, 2, and 3, because these are the 3 edges that are involved with the vertex V. For the directed graph, there are two concepts called in degree and out degree. In degree, or DEG minus V, is the number of incoming edges to V. The out degree, DEG plus V, is the number of outgoing edges from V. If we try to draw another simple directed graph, the in degree of V should be 1, this edge, and the out degree of V should be 2, this 2 edge. Next, we'll talk about handshaking lemma. What the handshaking lemma states, if we count the degree of all vertices in an undirected graph, you will get 2 times number of edges. To understand why it is the case, what this handshaking lemma for the undirected graph is telling us, we are counting each edge twice. So let's go back to our previous, let's say this is our undirected graph. and we want to count all the degree of all the vertices. So let's say this one is vertex 1, this is vertex 2, this is vertex 3 and 4. So what is the degree of vertex 1? The degree of vertex 1 is 1, 2, 3. What is the degree of vertex 2? Again 1, 2, 3. Similarly, the vertex 3 and vertex 4 has the degree 3 and 3. If you count all the degrees of all the vertices, you will get 3 plus 3 plus 3 plus 3 for this graph, which is 12. And previously we have calculated the number of edges in this graph is 6, which is half of the degree. For the directed graph, the handshaking lemma states that if you count the in degree of all the vertex and out degree of all the vertex, you will again get the twice the number of edges. If you think about why this is the case, let's draw a simple graph. So this is a simple graph with two vertex V and U, and we have only one edge. When we calculate the out degree of V, we'll count this edge. And when we calculate the in degree of U, we will again calculate this edge. That is why when we sum all the in degree and all the out degrees of the vertices of the graph for the directed graph, we will get 2 times E, the size of the edges. As I have told you in the beginning of the discussion, that in computer science, graph is a very important data structure. And a lot of problems can be modeled using graph. So to model some problems in computer, we have to represent the graph in some way. There are a couple of ways to represent the graph. We will talk about two of them. First one is adjacency matrix representation. So what the adjacency matrix representation of a graph G, which has a vertex set V and edge set E, is we will create a matrix of size V times V. It will be easier if we just take a look at one example. For example, we have a graph. If this is our graph with four vertex 1, 2, 3, and 4, and four edges between 1, 2, 2, 4, 1, 4, and 1, 3, we can represent this graph using this matrix. So we will create a matrix of size 4 by 4. Next, we will populate the cells using this formula. We will populate a cell Aij with the value of 1 if there is an edge between the vertex I and j. We will populate the cell Aij with the value of 0 if we don't have an edge between two vertices. Because we are talking about the simple graph, we don't have any loop. So all the diagonal cell will be populated with 0. That means we don't have any edges between 1 and 1, 2 and 2, 3 and 3, 4 and 4. Now we have an edge between 1 and 2. So 1 and 2 have an edge. Similarly, we have an edge between 2 and 1. So 2 and 1 also have an edge. Using this formula, we can populate the whole matrix. For this representation, the space requirement will be order of V square. The next way to represent a graph in a computer is using the adjacency list representation. For the adjacency list representation, we will create a storage for each vertex, and we will create a list for all the edges from that vertex. That is why we call this is adjacency list. So the way the same graph here can be represented as from 1 we have 3 edges 1, 2, 1, 4, 1, 3. That means 1 has connection or edge with 2, 3 and 4. Similarly, from 2 we have 2 edges between 2 and 1, 2 and 4. From 3 we have only one edge. From 4 we have 2 edges with 1 and 2. Using the adjacency list representation, it uses order of V plus E storage. You need one cell for each of the vertices, and then if you think about the representation here, we stored the same edge for the undiluted graph twice. Let's think about an edge 1, 2. This edge are stored in this representation twice. When we talk about from 1 to 2 and from 2 to 1. The quiz question for today's lecture will be you have to write down the advantage of these two representation and the disadvantage of these two representation. So this is your quiz question for today's lecture.